Hello, everybody, and welcome to Open Day 2020. It's a very different Open Day than what we all used to. My name is Christian Jacob, and I'm here with Nigel Tepper and Julia Arblaster. And the three of us are all staff at the School of Earth, Atmosphere, and Environment, and our general background area is atmospheric science. Julie, what is atmospheric science?
Well, it's really just weather and climate, I guess, if you're thinking of in layperson terms. And it's the kind of things that we do research on, or things that I do research on, are things like the El Nino Southern Oscillation, which you may have heard people talk about when we're thinking about Australian climate, and also things like the Southern Ocean and the weather systems that go along there that influence our rainfall in Southern Australia.
Yeah, my area is more on the weather side. I care about thunderstorms and how they work and what they do to the earth, both in terms of weather, and you all know what they do in terms of weather because every now and then we've got them in Melbourne, and you get a lot of rain and sometimes hail out of them. But it turns out they're also super important for climate and how the climate might change. And my special area of love and attention is building computer models that make predictions for weather and climate. And so we'll come back to that later. How about you, Nigel?
Well, I work in what would loosely be called surface-atmosphere interactions. And I guess I began rather as a boundary layer climatologist, where I was really interested in the impact, for example, that cities have on the atmosphere, particularly radiation transfers. But then I got into a whole lot of other stuff when I moved to Monash University, a lot of stuff around climate impacts. I worked on dust storms. I worked on air quality. I worked on fire. And most recently, I've come back to talk about work on urban climate. I'm going to talk a little bit more about that later on. But what I want to do now is ask, one of you, the climate's changing. So what does that mean? What's the latest news in this topic?
Yeah, the climate is changing, and I can share a slide on that because can everyone see?
Yes, very well.
As we know, in the last year, we've had lots of news about the climate, and I'm just showing here a time series of Australian temperatures, and you can see the last year that's indicated with that arrow was actually our hottest year on record. And so in Australia we have good records from thermometers since the 1910, and you can see it goes up and down and it varies from year to year, but you can see that it's been marching steadily upwards, and last year was actually our hottest year on record and our driest year on record. So yeah, the climate is changing both globally and in Australia. But of course we don't live on a temperature time series, and mean temperature maybe doesn't mean a lot to us because we live day to day. And so things that are the impacts of those temperatures are things like the extremes. So here's a figure from the Bureau of Meteorology on how the number of extreme days extremely hot days have really been increasing too. And this has really big impacts, of course, on how we go about our lives. If we have these really extremely hot days, it does lots of things to our infrastructure, like our train systems, and has really impacts on human health. And so these are the kind of things that we study at Monash and do research on, is trying to understand why the climate is changing, and then what that impacts on. And so here's just some of the things that we study at Monash, things like tropical cyclones and heat waves, like I said, droughts and clouds, how climate change is influencing all of these things that have real impact on our climate, on our lives here in Australia. Just stop sharing that. And then I guess that kind of builds into my question about how we really get at answering those questions about how the climate has changed. And Christian, I know you mentioned you have climate models. That's a passion of yours. So how how do we predict the future? How does it work?
Yeah, one of the fascinating things we do in atmospheric science is we look into the future. Not many people have the privilege of doing that. And of course, the running joke is that the crystal ball was a bit cloudy today, and so the weather forecast wasn't quite as good. But actually, we don't use crystal balls to make these predictions. We use modeling, and you hear a lot of about modeling right now, don't we? We hear COVID-19 modeling, and before that, we often hear about economic modeling and what the growth rate is and what the exchange rate will be. Turns out the models we use to make weather and climate predictions are quite different from a model that predicts COVID, in that rather than looking at past data and extrapolating from that past data into the future, we actually start with what looks like Egyptian hieroglyphs to most of you, I presume, a bunch of equations, mathematical equations, but they're actually quite familiar things to all of you who've done physics in high school. There's Newton's second law in there, there's the law of energy conservation, and so on. What we do is we take those equations and then we divide the Earth up into boxes. That's this picture in the middle, right? So, and then we calculate the temperature, the pressure, and all the things for each box. Turns out to be one of the most computationally expensive things you can cook up. And so to do it, we need a supercomputer, not just a little computer or a computer. No, we get supercomputers to do it. Ours sits in Canberra at the National Computational Infrastructure, and it's a very powerful computer. And all these things together, we can produce a forecast for the weather every day. And so here's one for tomorrow, Saturday and Sunday. Or we can also run these models longer into the future, and we can ask if the composition of the atmosphere changed, if we had more CO2 in the atmosphere, how would things like the global mean temperature change? And here's a result of this. And we have result from two different assumptions. The blue line is if we don't change the CO2 in the atmosphere much further than where we are right now. The red one is if we continue business as usual. And what we can see in one scenario, the Earth will be about 1 degree warmer by 2100. In the other one, it will be 4 degrees warmer. And it's quite an amazing thing to be able to do this, actually. And you can see how atmospheric science, just in this little slide, has mathematics and physics in it, has computational science in it. And then, most importantly, well, once we figured out it's going to be 4 degrees warmer, then what happens, Nigel? What impacts do we expect from, a 4 degree warmer world?
Well, that's really a major area of research in the atmospheric sciences at the moment. You can imagine that a 4 degree warmer world is going to impact on all sorts of things. We're going to have higher sea levels. We're going to have impacts on the biosphere. And some of the biggest impacts are actually going to be on humans. And that's one of the areas that we've been particularly interested in at Monash, particularly the impacts of climate change on cities and how we can better prepare cities for climate change. And one of the reasons we're interested in this is that more people die of heat, of the heat hazard, than any other natural hazard. Earthquakes, floods, cyclones, all of those things put together. Around the world, more people die of heat than anything else. And of course, with climate change, that's only going to get worse. So we've been working in this broad area for a while now. And let me just bring up a slide here. Okay, can you see that? I'll bring it up full screen. Yeah. So the work that we've been doing in this broad area began back about 10 or 15 years ago, where we did some of the early work for the Department of Health in Victoria on heat-health relationships. And one of the things we did was we looked at we looked at all of the mortality data over about a 25-year period on a daily basis. And we looked at the climate and the weather characteristics of the days. And we looked at what the mortality anomalies were on each day compared to what we would normally expect. And in the end, we found that a very simple relationship between temperature and mortality actually described a lot of what was going on in Melbourne and Victoria. And this has become the basis of the Victorian heat warning system. So just looking at this diagram, we can see that an average, note this is mean daily temperature. So it's yesterday's maximum or this morning's minimum. So over here we see that if we have a 40-degree day followed by a 20-degree night, then we have a mean daily temperature of 30 degrees. And what we find is that there's very little impact of changing temperature all the way up to about 28 or 30 degrees. And then we have a threshold temperature above which people begin to die at increasing rates. And in fact, above that temperature, the death rate in this age group, above 64-year-olds, which includes me now, increases by about 17% overall. But the critical thing to note here is that just reducing those temperatures by a little bit can save lives. And that's really provided guidance for not only for heat health warnings, but it's also a target for heat mitigation. So a lot of the other work that we've been doing in the last 10 or 15 years, and we've had the help of postdocs and about close to 20 PhD students, is to look at what we can do to reduce city temperatures so that we can save lives and provide a lot more thermal comfort. So we've been focusing in particular on the role of water and green infrastructure. That is things like increased tree cover and forest cover, green walls, green roofs, trees in the landscape, trees on the roadside, bioswales, increased water bodies, and so on and so forth. And what we've been able to do is look at basically at two scales. At the micro scale, we've been looking at ways of reducing air temperature and radiant temperatures to improve thermal comfort. So this is down here at the micro scale. And what we found is that we can reduce feels-like temperatures under heatwave conditions by as much as 10 degrees by providing more shade and providing cooling through evaporation, evapotranspiration. And then at that larger city scale, we can provide actual air temperature cooling of 1 or 2 degrees. And from the earlier work that we did on the sort of epidemiology of heat and health, we know that 1 or 2 degrees cooling on a 45-degree day or a 40-degree day is actually going to save lives. So that's pretty much where our focus has been in the last few years. So I guess that really we need to now think about what the opportunities are for students to actually come and join us to do some of this really interesting and we hope useful work on extremes, on modelling, and on adaptation to climate change. So perhaps I could throw the question over to the other two of you. What can we do here at Monash to help people with this?
So I think even this very short tour through our work has shown the breadth of the sorts of things you can do if you come and study weather and climate at Monash. You can do it in several ways. You can do it by studying meteorology, you can have a climate science degree, or you can study geography, and all of these connect you to these issues that we've discussed today. And I think for more information, I would direct the students to the brochures and also to the Open Day booths, which are online this year as well, thanks to COVID. Hopefully we'll see many of them around. What do you think, Julie?
Yeah, I think for those really interested in the topic, there's this, our major in atmospheric science, but in reality, I think climate change is going to affect any job that people go into. So even just getting a taste for some of our courses, you'll learn a lot about how the climate is changing and how it might change in the future. And you'll learn skills that I think are really useful in many different careers. So data analysis, big data that we use. Our climate models run on supercomputers. So you learn lots of varied skills as well as learn about something fun.
If you're not sure.
Sorry?
And perhaps I could just just jump in there and say, look, we've got opportunities in the school for people that come from all sorts of backgrounds. So I'm a physical geographer. So if you come more from the geography background, you know, there's a place for you here. If you come from computing or mathematics or other areas of the physical sciences, it doesn't matter. There's usually a place for you in atmospheric science.
And if you're not sure whether this is for you, I recommend you take the first year units that the School of Earth, Atmosphere and Environment offers and see how you like them. Where in those units, you'll get a very broad overview of all the topics that are covered, including weather, climate, and its impacts. And we even offer you a first year unit, elective unit on climate change and its impacts specifically. And that's targeted at any student because, as Julie quite rightly said, climate change will affect all of you, no matter what your job will be, no matter where in the world you will be, climate change will be with you. So maybe on that note, we should sign off and thank everybody for watching this video.